Assalamu alaikum. Welcome to lecture 9 on electric circuit analysis 2. I'm Dr. Khuram Naveed and I'm going to be your instructor in this lecture. So in this lecture we will continue to talk about AC power analysis. So particularly in this lecture we will talk about effective or RMS value of AC current and voltage. So the main idea of effective value is that we want to measure the effectiveness of a voltage or current source in delivering power to a resistive load. So basically what we want to do, we want to measure the effectiveness of the AC source in terms of its DC equivalent. So the effective value for a periodic current is the value that is equal to the DC current that delivers the same average power to a resistor as delivered by the periodic current itself. So what it means is if we have an AC source that is connected to this load uh, of resistance R, and we also have this DC source that is also connected to a load that of resistance R. So this DC current uh, um, can be termed as an effective value of this AC current if and only if the power delivered by this DC current to this load of resistance R is equal to the power delivered by the average power delivered by this AC source to this load of resistance R. Simply stated, it means that if power delivered by this this DC source and power delivered by this AC source to this load of resistance R is equal, then it means that we can say that this DC current is the effective value of the um, of this AC current, or in other words, this AC current is as effective as this DC current. So um, so uh, so let's move ahead and try to find expression for power for these currents. So in case of AC current, we know that we can write the average power using this integral over the interval of time 0 to capital T, where this capital T is the time period of the periodic AC current. So um, right, so we have this expression for the average power of this AC current, and in case of DC current we have this particular expression for the uh, power delivered by this DC current to this load of resistance R, to be specific. Okay, so we know that in order for this DC current to be an effective value of this AC current, power delivered by both of these currents to this load of resistance R must be equal. So we set them equal, or we equate them. Since this resistance R is not dependent on T, that means we can take this out of the integral. So we write it here. And since we have R on both sides of equation, so we can cancel both R's. And eventually we'll end up with this expression for I effective in terms of the AC current I. So as you can see here, the effective value of the AC current can be calculated by taking the square of the AC current and then um, taking its mean. As you can see, this is average operator. This is the uh, integration of the AC current over the interval of time 0 to capital T, and then this is the division by capital T, which makes it mean. And then once we have mean of the squared uh, AC current, then we take its square root. So this is how we calculate the effective value of the AC current, right? So we can also find out a similar expression for effective value of the AC voltage. Um, right, so let's try to decode it. As I've already told you, first thing that we do is we take the square of the AC source. So in case of current, we take the square of the current, and in case of voltage, we take the square of the voltage, and then we take the mean of the squared quantity by integrating the continuous quantity for the interval 0 to capital T, which is basically the time period, and then we divide it by the time period to compute its mean. So this is basically mean square, and then we compute its square root. That means the effective value of current is nothing but uh, the root mean square value of the AC current source. And similarly, effective value of voltage source is nothing but root mean square value of the voltage, right? So therefore we denote this I effective using this IRMS, that is root mean square value of current, and V effective with VRMS, that is root mean square value of voltage. So now we substitute the value of AC current in this expression. By doing so, we get this cos square term. So um, so what? So this cos square omega t can be written as 1 plus cos 2 omega t using the trigonometric identities, and by doing so, we get this expression, and we know from lecture 7 that integral of cos 2 omega t for this interval 0 to capital T is 0, and therefore we end up with this final term, that is Im divided by under root 2. So IRMS, root mean square value of the AC current, is basically the Im divided by under root 2, where Im is the amplitude uh, of the AC current. Right, so we can also find similar expression for VRMS in terms of Vm. So once we have these IRMS and VRMS values of AC sources, we can then move to represent this average power of AC source um, in terms of IRMS and VRMS values. So in order to do that, we can uh, write this 2 as a multiplication of under root 2 into under root 2, and by doing so we can write this expression like this, and that allows us to express average power in terms of VRMS and IRMS. So this is our average power in terms of VRMS and IRMS, and in case of purely resistive load, this is the final power in terms of IRMS and VRMS. Right, so we can rewrite this expression in terms of VRMS and IRMS, as you can see here. Since we are equating the power delivered by AC source with the power delivered by DC source, the power delivered by DC source is represented by as a multiplication of V into I. So this particular multiplication can be seen as the equivalent DC equivalent of the power delivered by the AC source. So therefore, this we call this as apparent power, that is S, which is equal to VRMS into IRMS. We call it apparent power because this is not exactly the actual power delivered by the AC source, because the actual power delivered by the AC sources also has this factor cos theta V minus theta I. So therefore we call this apparent power, that is power we think that this AC source may be delivering. So this additional factor cos theta V minus theta I is called the power factor of this average power, and we write this average power as a function of parent power S, like this, where this factor theta V minus theta I is the power factor, uh, and it is the cosine of the phase difference between the voltage and current, um, and and it is defined like this using average power and apparent power. Basically, when you divide this P by apparent power, so this part will be cancelled and you will be left with this part, and that is power factor. So another way to look at it is that this angle theta V minus theta I is the phase difference between the voltage and current, and we get this situation where theta V is we're subtracting theta I from theta V when we divide voltage by current, and that means theta V minus theta I is the argument or angle argument of the impedance. Right. So this so this is basically um, what we need to know about the parent power and power factor. So in this particular example, we need to determine the RMS value of the current waveform in figure 11.14. So so this is the current, and in order to be able to find its RMS value, we first need to write it in mathematical form. So as you can see, this is a ramp function, um, and so its slope is 5, because the 10 minus 0 divided by 2 minus 0 is 5. So so this is 5t during the interval 0 to 2, and from interval 2 to 4 it is minus 10, and after that it is repeating itself again and again. So basically we need to write it for the one interval, which we have done here. So now we put this value in this expression, and we see that we have two parts. First, we integrate this function for time 0 to 2, and in that case we have I of t equals to 5t, and in the next part we integrate this function for time between 2 and 4. So in this time the value of current is minus 10. So when we integrate the square of current for these intervals, we end up with this value, and then we also divide it by 4. Okay, so once we obtain this IRMS, we can then use this formula to find the average power dissipated by a 2 ohm resistor. Okay, so now we have another example. A series connected load draws a currents I of t 4 cos 100 pi t plus this 10 degree of phase, and we have a voltage that is 120 into cos 10 cos 100 pi t minus 20 degree of phase. So find apparent power and the power factor. So apparent power is basically the multiplication of the root mean square values of the AC current and AC voltage. So the root mean square value of current can be obtained by dividing the amplitude of current with under root 2. So this is exactly what we do. We divide here. We are dividing this amplitude of current by under root 2. And root mean square of voltage can be obtained by dividing the amplitude of voltage by under root 2. So exactly this is what we are doing here. And once we have these root mean square values for voltage and current, and so then we multiply them to obtain the apparent power, which is 240 volt ampere. And the power factor for this particular uh, source is, so first we need to find the angle argument. So we have, this is the phase of voltage, which is minus 20, and this is the phase of current, which is 10. So the angle argument theta v minus theta would be minus 20 into minus 10, and then we take its cos, and we end up with cos minus 30, which is equal to 0.866. And it is leading because the overall angle of the angle of the argument is minus. And if the angle of the argument is positive, then it means the power factor is lagging. Right, that's it for this lecture.